on solubility rules, which was essentially determining whether or not a compound, when we throw it into water, whether or not it is soluble, breaks apart, or not. We also said that you can bring two individual ions together, and when they connect with each other, you do a solubility check. And the solubility check is, if it's soluble, nothing will form. If it's insoluble, it'll form a precipitate. And we're really interested in precipitates because that's what net ionic reactions are. So what we're going to do right now is I'm going to give you a series of problems. Did we start you off with a problem on the net ionics last class period or no? We did not? All right, so I'm going to switch to your screen on the board, and I'm going to give you a series of practice problems that are net ionics. Just let me know here when you have, can you guys see it? Anyone that has their screen up, if you can look and see if, is Leo being shown right now on your screen? Okay, so let's do this problem, and I'm going to give you the word equation only on the left-hand side. So let's go magnesium sulfate aqueous AQ as a little subscript in this. So right next to the sulfate, just write AQ kind of down below. Plus calcium nitrate soluble and an arrow. You need to write aqueous next to the calcium nitrate. Now, just as a reminder, aqueous is dissolved in water. So what that means is this. If you put your finger on magnesium sulfate, please. What that means is that even though I've written it as magnesium sulfate, that AQ means that those are actually ions that are dissolved in water. We've written them together, but really what that is Mg2 plus and SO4 minus floating around in water. We could have written it as magnesium ion plus sulfate ion. In fact, let's write that as formulas down below. Can you write Mg2 plus underneath and a little AQ subscript plus SO4 minus with an aqueous subscript plus Ca2 plus aqueous and plus NO3 minus aqueous. Now, what that means is that all four of those ions are just floating around in the water together. And as they float around, would you acknowledge that they're going to come in contact with each other and hit each other? Now, if you wanted to follow the rules, see where it says aqueous above? Can you put magnesium sulfate, put your finger on aqueous? You realize if we wanted to, we could look at the rules, couldn't we? And couldn't we find the rule that says sulfates are always soluble except with Cal-Bear peanut butter? And isn't magnesium not part of that? So wouldn't that be soluble? That's why it's written as aqueous. Same thing with calcium nitrate. Isn't the rule nitrates are always soluble? So we know that if magnesium and nitrate, can you put magnesium and sulfate down below? Can you put your finger on one finger on each one? If they're to come together with each other, they can come together. The rule is, and they've already told you in the problem, is that they're soluble. So they won't do anything, agree? Same thing with the calcium and the nitrate. How do we know that it's soluble? Well, we could have done the rules for it, but don't they tell you that it's aqueous? So what we're going to try and do is we're going to try and see what are the other options for things knocking into each other. Now, let me remind you of two immutable truths. One, positive ions will never hook up. Two, negative ions will never hook up. Remember, you can't have a positive and a positive and a negative and a negative. Can I get a head bob around the room if that makes sense? So if we look at the actual options of what ions have a chance at hooking up, can you put like a swoopy arrow, a double arrow underneath magnesium going to nitrate? Okay, that is a good swoopy arrow. Also going back to magnesium. Arrow on the magnesium side.
We need a vote on fire.
Remind me as soon as I get in the lecture, you're going to be my like, hey, remind me. Okay, good job. And then isn't the other option going to be SO4 minus and calcium? Can you put a double? Can you do a swoopy arrow for those? Now, in essence, this looks a lot like foil. You guys ever done foil in math? Yeah. This is essentially foil. The first thing goes to the last thing. The two middle things hook up with each other. So what we're going to do is this. Every time that we have two ions that can try to hook up with each other, we're going to do solubility rules for them. So let's try Mg and NO3. You put your friend Mg, one finger on Mg, one finger on NO3. Do you realize that those two things are going to try and hook up? They're going to bang into each other. Let's put it that way, right? So let's do a solubility rule for that. Is there any rule that applies for anything with Mg or NO3? Nitrates are what? Always soluble. So if nitrates are always soluble, doesn't that mean that no matter what I put them together with, they're not going to hook up? So that makes them spectator ions. They'll still float around in there, but they're not going to be involved in our actual equation. So can you put a slash through the NO3 minus and a slash through the Mg2 plus? Those are not going to be involved in forming a precipitate. Now, our job is to write the net ionic equation. And what a net ionic equation is simply writing the things that are involved in forming a precipitate. In fact, that's our goal. And if you think about it, if you look at in finance, net versus gross, isn't gross everything that you make? And isn't net everything minus the expenses and whatnot? It's what the actual important is the net. So yeah, you can make $1 billion, but if you spent 999 million, you didn't really make very much, right? Well, the same thing here. We only care about the ions, we're ugly this way, that are involved in forming a precipitate. So understand that occasionally all of the ions are going to be soluble. So no matter what, nothing's going to form, and we write no precipitate. So you understand that's an option. Option number 2 is that 2 ions can combine and form a precipitate. Option number 3 is that all 4 ions can interact and you end up with 2 precipitates. That's kind of rare, but it happens. So let's look at our other pairing here. Calcium and sulfate. Aren't calcium and sulfate going to potentially hit each other in the water? And when they do, we're going to do a solubility check, right? So let's find the rule. What rule is there that relates calcium and sulfate? Sulfates are soluble except for cal, bears, stir, peanut butter. Isn't calcium part of that? Yeah. That means that it is insoluble, and we collectively in our heads cheer out loud because that means we found a precipitate. So what that means is that let's go underneath that. We're going to write only the ions that can form a precipitate. Now I always like to do this. I'm particular this way. You could write SO4 2 minus plus Ca2 plus and then write what the compound is on the other side. But I like putting the positive ions always first. So can you write Ca2 plus? No, underneath it. Ca2 plus SO4 2 minus, and then put an arrow. And literally on the other side, we're just going to write the ionic compound that's formed when those two are hooking up. So wouldn't a 2 plus and a 2 minus, wouldn't they cancel out or smush together? So when we end up with CaSO4, can you box that for me? The whole thing? That is your net ionic equation. And this is like a sample of what your test question is going to look like. Literally, it's going to look like this. Any questions? Let's try another one. Oh, and by the way, with these, it's kind of cool because you do not have to put the word equation on the product side. Literally, all I want are the net ionics, is the net ionic equation. That's it. Okay, let's try another one. Let's go. Zinc acetate, aqueous. Now, by the way, by default, all the reactants must be aqueous because if not, they don't form ions. They wouldn't form ions, and they can't form anything else. Plus hydrochloric acid. Yes. By the way, that's a hint because isn't hydrochloric acid a strong acid? So it's everything that's going to be. So if you ever see a problem where accidentally the AQ has been left off, you need to make sure that you understand that it actually is together. Now, I want to show you something that's kind of cool. You can write all the ions underneath, or you can do it just from the equation itself. Like, what is zinc going to try and hook up with? Right, but what part of the hydrochloric? Well, let's do this. Let's do the ions first before we do this. So let's write Zn2 plus C2H3O2 minus plus H plus Cl minus. Let's FOIL this.
Wait, do we need aqueous?
You do. Right now, just, yeah, we're fine. Assume that they're all aqueous because they are all aqueous. Now, you realize you could have done the same thing with the actual equation up above. Can you write a Zn to the Cl? Zinc, like above it, zinc to the chloric. No, don't actually write the Zn, but I just want you to write it from the actual word zinc. I want to show you how you could do it just from the actual word equation. So zinc to chloric, and then couldn't you write hydro, the acetate to the hydro? Now you have to be aware that hydro is short for hydrogen and chloric is short for chlorine, which is what we've written underneath. Are you with me? So let's go through the rules. Zinc and chloride, aren't they going to try and hook up? What's the rule that applies for this? Not Cl and Zn. That's what we're trying to hook up. Yeah. So watch. You have Cl minus and Zn2 plus. They're trying to hook up with each other, right? So we've actually got to do a. I got to take this. Oh, I missed it. My doctor. The Zn and the Cl. Sorry, I just lost my train of thought. We're going to go to them, and when they hook up, we're going to go, what rule applies? So we're going to go through, is there an acid? No. Is there a base? No. Why? Because there's not an H or an OH involved with ZnCl. Are you guys with me? So then we go to the Nag's tag rules, and we go all the way through to group 7. And isn't the rule for group 7? Group 7s are soluble, except for PMS. The other group came up, one of my other classes came up with a much better one. And I can't remember what it is anymore.
Oh, no, he did. It was.
Oh, yours was weird. Put away a case. Another class actually came up with something like, I wish I got it. Anyway, so in this case, is Zn part of the PMS? It's not. Therefore, this is going to be soluble. So if those are soluble, then that means those two things are going to be spectator ions. Can you put a line through the Zn2 plus and the Cl minus? Does everyone understand what we're doing or see what we're doing right here? Okay, that leaves us with H plus and C2H3O2 minus. Isn't the first rule about acids? So we look at hydrogen and acetate, and we say to ourselves, is that part of CBS pin? No. It's not. Only CBS pin is soluble, right? In this case, this is soluble. Or sorry, this is insoluble. Well, I didn't misspeak. So wouldn't that mean that those two are going to hook up and actually form something? So let's write the net ionic below, and let's write the positive ion first. So we're at H plus C2H3O2 minus.
Are the two outsides always crossed out?
No, that's a fluke. Totally a fluke. I just happen to give you two examples. In fact, I'll try and make sure that the next example doesn't have that. And what is that going to form? Will that form HC2H3O2?
But aren't all acetates soluble?
Ah, yes, they are. But look at your rules. Isn't the rule that says that all acetates are soluble? Isn't it the C rule?
Yeah, that's up there.
We apply the rules in order. So if there's a hydrogen, the hydrogen takes precedence over the acetate rule. Good thing that isn't at all distracting. Does that make sense, woman?
Yes.
And does everyone get that here? So that's going to be our balanced equation for our net ionic equation. Now, I could give you guys samples where they're both reacting or where they're not, neither of them reacting. So maybe I will. Maybe I won't. Let's try one more. Any questions, by the way, so far? Can you affirm this for me? Can you affirm that really this test is about knowing your solubility rules? If you know your ABCD, then this here is really just not that hard. Yes, Randall.
Do you have to do any balancing?
Yeah.
Well, I mean, like on the first step when you said Zn2 plus C2H3, it should be 2 C2H.
Yep. But we only worry about the ion. So watch. His question is, do we have to worry about balancing? And absolutely. So if I have Mg plus Cl minus, right, it's going to form MgCl2. So I really, in my balanced equation, I need to write Mg plus 2Cl minus goes to MgCl2. right? But I don't need to see it balanced when you write it from the original equation because all those are just ions floating around. We only care about the net ionic equation. Let's try one here. Let's go aluminum nitrate plus cobalt 2. Let me switch that. Not cobalt 2. Let's go calcium. Nope. Let me switch it again.
Oh.
Sorry. I'm so sorry. You do this in your head. Try. I'm the teacher. I should be able to do this. Let's try potassium oxalate. I just wanted to find one that meets up with her criteria of being this. So I wrote it wrong a couple of times. All right, they're all aqueous, right? Can I show you something that's kind of cool? Let's just do the FOIL with the words. So put aluminum to oxalate and potassium to nitrate. Do you realize we can follow the rules without actually having to write the ions out first? Shall we? Let's take a look at aluminum and oxalate. Can you find a rule?
No.
No rules, right? So it goes to the rules part 2. Rules part 2 say, if none of the other rules apply, -1, we look at the negative ion only. -1 is soluble, but aren't -2 and -3 insoluble? So in this case, what's oxalate? It's a 2-. That's good. That means it is going to be insoluble. Those two are going to hook up. Agree? So we're going to keep that in the back of our hat, and then we're going to go to the other one just to see if the other one forms. I don't know why we'd keep it in the back of our hat. That's just, I think I misspoke on the expression even. But thank you for pointing out my failure. That's delightful. Thanks, Sam. Potassium and nitrate. Is there any rule that applies for potassium and nitrate?
Yeah.
Nitrate is also always soluble. And just in case you're like, I don't remember the nitrate rule. Boom! Group 1s are always soluble. Aren't both of them solubility rules? So as soon as you can apply one rule, can we put a line through the nitrate and the potassium? So I'm just showing you how you don't have to write the complete ionic equation. By the way, what we've been doing before, we write all the ions down below. That's the complete ionic equation. We don't have to do that. But right now, we have to write what the ions are, right? So what's Al as an ion? It's going to be right, Al3 plus. And what's oxalate? C2O4 2-. And when we put them together on the other side, can you put an arrow? Wouldn't that give us Al2, C2O4, in parentheses, 3? Now, this is getting to Randall's question here. So first of all, did you see how the outside ones actually reacted this time? And then 2, this is not a balanced net ionic equation yet. So if you write that, you're not going to get all your points. You need to write the coefficients in front of each one. So don't we need a 2 in front of the Al and a 3 in front of the C2O4? Now box that whole bad boy. That is our net ionic equation.
I like this is great. I was pondering your greatness.
I sense the sarcasm even there, but I'm going to let this one go. All right. Any questions on this? So essentially, literally, well, essentially, literally, I don't know why I use those two together. You want any comment on essentially and literally together? Sure you don't want to critique me. Essentially, what we're doing is we're just doing a double replacement reaction, and we're seeing whether the ions that form are soluble or insoluble. Now, I've not given you an example on this, but you will run across occasions where neither of the two of them will hook up, in which case you don't write any ions down below. All you write is no precipitate. You, then you, then you.
So I don't think box that as the final one. Do we write any like AQ?
Okay, so yes. So you need to write AQ and AQ on the left-hand side. And then on the right-hand side, you need to write an S for solid. Now, here's the problem, is that a precipitate can either be a solid or liquid. So occasionally, or even a gas, we don't really know what the states of matter all are. So as long as you put aqueous on the left-hand side, I'll be good. Typically, it's going to be a solid that's formed as a precipitate, but you could also have a liquid as well. Yes, Reagan?
So is it still considered insoluble if part of it is soluble and part of it is insoluble? Like, what would you call it?
No, it's kind of like skydiving. You can't kind of skydive.
Okay.
As soon as you've left the plane, you're skydiving, right? So
Yeah.
if you look at a compound, you can't be half and half. The compound's
Yeah.
either soluble or it's not. So when we look at the rules, if one of the things in the compound makes the compound soluble, it's a soluble compound.
Okay, so this is still soluble.
What example are you talking about here?
The one we just did.
Well, which part?
Oh, I see what you're saying. It's different parts of it. Okay. So
I don't know. Can you clarify?
I was just asking about the whole equation in general. Like, you can't say that it's all soluble or all insoluble.
Well, what I can say is that aluminum nitrate, since it says AQ next to it, it's soluble, which means that it actually breaks apart into ions.
Okay.
I can say that potassium and oxalate are soluble because I looked at the rules for that. But then when I have to mix and match the rules, I have to apply the rule every single time with two new compounds.
Yeah.
And if one of the rules can apply to two, now, by the way, you realize solubility rules is never just one ion, because if it's just one ion, it's soluble.
Yeah.
Soluble means dissolved in water. So if I tell you, hey, I have just an oxalate ion, you can't say it's soluble or insoluble, because if it's just an ion, it's floating around soluble. Do you guys track this here? The only time we care about soluble or insoluble is when we take that oxalate and we put it together with a positive ion. Then we have to determine whether it's soluble. So you're never going to do a solubility check on one single ion, because that one single ion by default is soluble. It's floating around dissolved in water. Randall.
So we don't have to write any subscript for the right part of the.
For the right part of the equation, yeah, Al2 C2O4 in parentheses 3.
Yeah, but like, I mean,
Like
like,
the aqua.
Oh, sorry. So like the aqueous. This is where I'm kind of cringing, because you're supposed to. You should have write it as solid or liquid. But for right now, I'm just going to assume that if you put a compound on the other side, that it is a precipitate. You aren't going to be expected to memorize which things are solids or liquids at room temperature. I mean, if you wanted to, and you wanted to put solid on the end of each one, I'd probably be okay with that, because it's forming a precipitate, but not all precipitates are solids. For example, if I put H plus OH minus together, let's do this real quick, right? H plus OH minus. In fact, let's do this way. Let's go hydrochloric acid, erase, and I'll give you an example. So, right, hydrochloric acid plus calcium hydroxide. To foil it, just using the words, it's kind of awkward, because hydro, some of you guys aren't going to realize this, the hydrogen ion, and chloric, some of you guys might not realize that it's Cl minus. So let's just write all the ions down. Wouldn't that be H plus and Cl minus? And then wouldn't that be Ca2 plus and OH minus? Now, you do understand that I'm ignoring the fact that CaOH in parentheses 2 is actually one Ca2 plus and two OH minuses, right? Because I know the OH minus is going to try and hook up with something else. Do you guys follow this here? So we don't care whether that's 2 or 1. But show us the FOIL. Okay. Let's start off with HOH. Yeah. Isn't HOH, don't we follow the A rule? So we look at the A rule. Is OH minus part of CBS pin? No, that means that it's insoluble, which means it will form HOH or water. Let's look at the two middle ones, calcium and chloride.
they're also insoluble.
Try again. Chloride, isn't that group 7
Yeah.
in NAGSAG? Group 7 in NAGSAG is soluble always, except for, as I cringed, PMS, right? So is calcium part of PMS? No. So therefore, it's going to be soluble. I should have made this example one where the two middle ones are insoluble as well. You realize that both pairs can be insoluble? It'll happen. It's not common, but you're going to see them. Don't get freaked out. Just make sure you know your rules, because if you make a mistake and say that calcium chloride's insoluble, then you're going to get it wrong. Yes, sir? You'll have a periodic table. You'll have a periodic table. So you can look at that if you want. But honestly, after you've done a few of these, you're going to recognize, especially when you do these worksheets, you're going to love chlorides, you're going to love nitrates, you're going to love group 1s because those are just hack. In fact, in most problems, you'll be able to slash off 2 of them almost immediately because you look at it, a lot of group 1s are involved in the original equation because that makes everything next to it soluble, right? So that means that if you have a sodium, it's never going to hook up with anything, so you can just hack it out of your equation. Yes, Hannah?
So we get a periodic table for some.
Okay. Yes. In fact, I think I've given you a periodic table. If you want to bring a periodic table with you, I'll try and remember I keep every test I keep on giving you in the back.
So
yes?
What this is
no, I don't want to listen to you. Go. Oh, make some more fun. Make some more jokes about the teacher.
We have more time on the quiz tomorrow.
Yes. Yes. Anyone else? Anyone possibly else that wants to ask a question? Anyone that's not there? Yes, Ryan.
So is there any like know all the rules except for memorizing?
Well, here's the thing. You know what you would have had to do prior to my ABCD rules? You would have had a long list of just all the things written down. Sulfates are soluble except for this, and there would be no order in it. So it would have been, I designed this to make it try simpler. Honestly, by the time you've done the first worksheet, I'm going to give you like 3 or 4 of these. By the time you've done the first worksheet, the rules are going to be pretty cemented in. Okay, I guess I will finally accept Mr. Sarcasm.
What this is saying is that water is insoluble in water.
Yep.
Okay.
Yeah, what it's saying is that water is a liquid, right? So you can't have water dissolved in water, right? So water is the liquid, it's insoluble, right? So none of us would be like, oh, you know what I'm gonna do today? I'm gonna dissolve some water in water.
Yeah.
No, you're just putting more of something that's insoluble into it. Yes.
Are we ever gonna have like problems where it's like saying like hydrochloric acid, for example, and saying whether it's gonna break up or not?
Sure. That's kind of like what your solubility quiz is gonna be next class period. Well, the more I think about it, I kind of like the idea of a net ionic quiz. Well, thank you, Randall. I did not think of that until you mentioned that. All right, so if you take a look at this right here, is that balanced off to H plus OH minus? It is. Although I was just going to talk about the test. Can you hold on 1 minute here? All right, so your homework for tonight is going to be net ionic equations worksheet 1, and I'm probably net ionic worksheet 2, which I'm going to give you. You're going to discover really quickly that after you start doing some of these, it's very fast. So I'm stopping broadcast.